Today's lecture, we're going to cover how to set up a 2D single view vision process using a fixed camera mount for our robotics. We'll go through some slides to kind of explain how the process is going to go and some of the things that we're going to do with our robot, and then we'll actually have Merrill come up and start the 2D single view vision process for us. All right, so a brief overview of what a 2D single view vision process is. It detects the position of a part and then compensates for the position of the part in the XY direction, as well as with some rotational motion in your R axis, which is the rotation about the Z axis. Since robots move in the X, Y, or Cartesian coordinate system, okay? And then cameras identify parts using pixels. We got to have a way to tie X, Y coordinates to pixel locations, all right? So this is what the 2D vision process will help us do. We will be using a fixed camera for our lab purposes. You can do this with a robot mounted camera, but our search cell here has a fixed camera. It's an XC56 Sony. It's got a 6mm lens on it, and our approximate standoff distance from the camera down to our surface where we're going to be identifying our parts is roughly 725mm. So what this is going to do, once an image has been captured, it's going to yield either a fixed frame offset or a tool offset. So that will be an offset relative to a specified frame or a specified tool. Okay, so our lab, we were going to be using a fixed frame offset. Okay, we're going to establish a user frame in the process, and then all of our offsets will be relative to that frame. Okay, so that's our specified frame. So again, the process that you're going to see with this lab, we're just going to verify that our user tool has indeed been established. We're not going to go through and show you how to establish that. That's already been done, but we are going to verify that it is accurate. We're then going to establish the user frame that we will be using in our vision process. It's very important that be identified. Then we're going to go into our grid calibration. This is how we tie our camera to the robot so that they're both speaking the same language. And then we'll go through the 2D single view vision process. So this will be where Merrill has to come over and access the robot's web server and then set all his parameters that he's going to need to execute this vision process. And then once that part is done, we'll do a program creation and then test the program. The one thing I do want to mention, whenever you're using vision systems and robotics, one of the key elements in your vision process is lighting. Our conditions here in the classroom, we're just going to be using ambient room light. Typically in an industrial setting or manufacturing setting, you would use dedicated illumination, specifically LED lights if you got them. All right, so the two frames that we're going to be using in our program, you heard me mention them earlier, are our tool frame, which was established using a 6-point method. Again, we're not going to show that process, but we will show the result of that process. And then a user frame, okay? And we're going to use a 4-point method to identify where this user frame is to our vision system. I'll probably refer back to this slide as we go through the process. Because there's some critical information that needs to be expressed when we do this process. And notice I've got it highlighted in red over here. Once we put our calibration grid in position to set up our user frame on and then do our grid calibration, cannot be moved. If it gets moved, then you got to start all over. The other thing is when you use these calibration grids to help calibrate the camera to the robot, you want your grid to be at or near whatever height your part is that you're going to be looking at. We actually have our grid, it's on a backer board that's about 12mm in thickness. It just so happens that a part that we're going to be using is 12mm in thickness as well. So we should be good to go there. So again, all of these things we're going to do step by step. So once we have our user frame set, then we can go into grid calibration. This is where we actually tie the the robot's XY coordinates that it uses to move around the work cell to the camera's pixel locations, okay? So that's what the grid is going to do. If you see the imagery up here, we have a grid that has a 30 millimeter spacing, which means each dot on this calibration grid is 30 millimeters from the other one. So as the camera takes an image, there is a pixel location on the camera imager chip that will be tied then to the XY coordinate on your robot. So this is how we tie these two elements together, is with this grid calibration. So again, if you look at the definition there, it's basically the process of mapping real world coordinates to the location of observed objects in the camera's view. So that's tying pixel count locations to X and Y locations. All right, so we're going to go back and have Meryl come up, and we're going to start this 2D single view process. The very first part of the process is to set up a camera. We're going to use one that has already been set up. It's a very simple process. So we're going to go ahead and start with the next step, which is our tool identification. We're going to set up a little fixture, and then Meryl's going to check to make sure that the tool center point is accurate. All right, Meryl, come on up. All right, so what Meryl's doing here is we're going to verify, again, where the tip of this little yellow pointer that we have in the gripper is. So this will be the tool that we use to establish our user frame that the robot will use during the vision process. So if it's accurate, he'll bring these 2 points together, the point on the obelisk and the point on the pointer, and jogging about his J4, his J5, and J6 axes, it should rotate about the obelisk and maintain its position. All right, so we can see now, as we're having our rotation, that the pointer that's being held by the gripper, all right, come back this way, is maintaining its position. It's not moving off the pointer of the obelisk. All right, from right here, let's put some J5 in it. So you can tell that our pointer is still maintaining its position. Okay. All right, from this position, let's put some J6, rotate about the J6. All right, so that looks good. Typically out in an industrial setting, you would have much more precision tooling to do this with. But for the tooling that we have in our lab here, this is what we've been working with, okay? So I think we have a good tool center point established that we can use to help establish our user frame. The next thing we're going to do is get ready to establish this user frame that we're going to use in our vision process. A frame is basically just where 3 axes come together, X, Y, and Z, that creates an origin point. So what we're identifying what our user frame is going to be is kind of you telling the robot where you're going to work. All right? We have a pretty big cell. It could go anywhere, but we're going to kind of isolate where this work is going to be occurring at. This is the calibration grid that we're going to be using for our lab assignment. This is a 30 millimeter grid spacing. So you can see we've got lots of dots on here, and this is what the camera sees. Notice we have a lot of contrast, okay? We have dark colored dots on a light colored background. Makes it real easy for the camera to see, okay? So the more contrast that we can create, the better our chances of improving our vision process. So we'll set this up, and once we have it set in place, we'll try not to move it till our grid calibration portion is over with. All right, he's going to set this up, turn the camera on with his laptop over there. He's already accessed the web server for the robot. So he'll turn the camera on, and then when he has his camera on, he can position this calibration grid where he wants it. Once that's done, then we'll move into our user frame setup for our calibration grid. All right, so now we can position our grid, and we'll put this row right on our crosshairs.
All right.
Oh, come down just a little bit. All right, to your up just a hair, and to your left just a little bit. All right, so we have our user frame number that we're going to use. And we're going to be using orthogonal projection, right? Because our part is flat. We don't have any Z height, part Z height, so we're going to be using orthogonal projection. All right, so let's look at, yeah, go ahead and locate it there. All right, so let's look at our data. All right, so our mean error value is 0.263. That's pretty good. Our aspect ratio is almost 1, so that's good. So I think that's a good find there. All right, so what Merrill's going to do now is we've kind of trained in this grid, and he's identified what frame number that we're going to put on this calibration grid. Okay, this frame number is the one that you'll see in the Vision program when he goes to execute it. Okay, so we have to identify the correct tool number as well as the correct frame number. So you can see from the PowerPoint on the board there, we're going to identify 4 points on this grid. We're going to identify an origin point, an X positive direction, a Y positive direction, and then a system origin point. So once these points are then defined, then our user frame will be established to this grid here. So typically when you're doing this out in the field, depending on how much experience you got, this is a relatively slow process. You're trying to get as accurately positioned as you can to identify where these points are. The more accurate you can make it, the more success your vision process will have. Okay, so he has identified his origin point, or the origin for this frame. Now he will move the robot to identify the X positive direction of our frame. So he's now defined his X positive direction. So now he'll go in and define his Y positive direction, and then a system origin point. Once this calibration grid is in place and you start using it for finding your user frame as well as your grid calibration, don't move it. And it has to be at part height or pretty near to it. All right, so we've accomplished the first couple of items on our process steps. We verified our user tool that was accurate setup, and we've just established the user frame that we're going to be using in our vision process. And the next thing we're going to do is calibrate our camera to our grid here, and this will then tie the user frame that we just set up, camera and robot. All right, so we've gone in and verified our grid calibration. The key elements that we set up in the grid calibration here using a web server was identify which frame we were going to be using. I'll go back to that setup page. That we're going to be using our vision process, and then which projection type that we're going to be doing. We're not going to be doing the perspective, we're going to be doing orthogonal, which means it's a flat surface, okay? The next part, which is going to be our 2D single view vision process, this will be a lot of web server interaction over here on the laptop. But now that we have used our calibration grid for both our user frame setup and our grid calibration, and we have saved that information, we can move it now. We're going to try to locate this part right here in our 2D vision process. And we're going to train the camera to look for this part. And we're going to do that by using a locator tool. It's called geometric pattern match. All right, it's basically going to create an edge along all the outside perimeters. Any detail that the camera can see, it'll put an edge on it so that the operator can identify where we want to have the robot sort of pick this part up, okay? We'll have this in our field of view, and we'll kind of do it the same way. We'll position our part in the field of view, and then we'll come over here to the computer and start filling out some of these parameters that will help us identify what this part is. What's the next one? Our vision process setup, right?
Yes.
All right, so let's go ahead and pull that tab up. All right, so we'll pick our camera that we've already established right there. All right, so let's go ahead and alter our exposure time. Let's darken it up just a little bit. Okay. All right, let's see if we can get it identified for our frame that we're going to use. So let's go ahead and turn our crosshairs on, and let's see if we can get our part located as close as we can.
All right.
All right. Up just a hair. Oh, right there. We'll go with that. So we've identified the camera that we're going to use. We've set our exposure time, offset mode. Again, this is a fixed frame offset, so whatever offset it creates, it will be relative to a frame, not a tool. Okay. We've identified the user frame that we set up earlier. These numbers have to match. Okay. So let's go in, now that we've got this part filled out, the rest of these fields we're not going to alter for right now. Let's go in and look at our locator tool, and let's teach our part here. Okay. So let's go ahead and set the origin that we're going to use. In this instance, let's move it up here. That will be our reference position there, our origin for our part. All right. Let's train these 4 circles here. We'll mask those so that it's only looking at this one. Okay. Let's look at this tab here. All right, so to make the, if you need to make it smaller, you click on that, then there you go. Now grab the center one and move it around. Okay. All right, so now we have put a training mask in there so that we'll not look for these here. We'll only look for that one. So let's make that an emphasis area. We'll put an emphasis area around that circle right there. Now when we do that, when we use an emphasis area, depending on how complex your part is, it may add time to the process, cycle time, okay? So let's go ahead and do a snap and find. Okay, so you can see we did a snap and find, and we got a score of 100. That's a good number. Okay, so any number up in the high 90s with 100, those are excellent scores. All right, so let's cursor down and look at the rest of our tabs. I don't think we'll alter those. These are default settings. We're going to go with those for right now. Your contrast threshold, your score threshold. We'll leave that at default settings for right now. All right, let's go back to our 2D single view process. All right, let's cursor all the way down. Now, hold on. So before we do a set, we got to do a snap and find and see what. All right, so again, we got a good score. Now we can set our reference position. Okay, so once we have done this part and we've set our reference position, you can't move the part. So as you're navigating your robot around your part to teach it points and positions, you can't hit the part or move the part. If you move the part, you got to go back through this process again, because now your reference position is no longer valid. Does that make sense?
Yes.
Okay. All right, so we have all of our information set correctly. Everything is turned green, which means it's been trained. It's got the information that it needs. So before we go to the next step, we're going to save this process. Now that we have those elements identified, we are going to step through this program and see if, in fact, our robot will move to the location that we identified in our vision process setup. All right, so step through it. As expected, our robot did move to the position that we had identified in our vision process setup. The real test comes now when we actually move the part from the reference position that it was in when it was taught. Okay, so hopefully, if we did everything correctly, as we move it, we're going to start by moving the part in the X and Y first, and then we'll give it some rotation to see how it does then. So now we'll move it from its reference position and see if the offset is then registered, and the robot will read the offset and move to the new location. Okay. All right, Meryl. So just move it in X and Y some distance from where it is now. So here's where our vision runtime screen will come into play here. So as Meryl is stepping through this program, the vision runtime screen will update and locate the part, and it will return a score. So if we got a good score, then our robot should move to the new position. All right, so let's move our part over here on this side in X and Y. We'll try it one time, and then we'll put in some rotation. So what I like to do to test our process is I like to move the part on each side of the robot just to see how the offsets are executed. So typically in X and Y, it executes really well. All right, Meryl, let's give it some rotation. So not only have we now moved our part in the X-axis and the Y-axis, now we have rotated this part about the Z-axis, okay, which is our roll, our R value. So now you will see as the robot moves into position that now our gripper will turn in relation to how it was when it was taught. And so we're moving into position as expected. All right. So let's move it on the other side and do it one more time, and we'll run it one time in the automatic mode. How about that? All right. Let's make sure that we are in our reach of our robot. All right. Very good. So even though in this application, our camera's field of view is so much larger than our robot's reach, so we have to be cautious about where we place our part inside the field of view. All right, so we got some rotation in, and our robot moved to our pick point. Okay. All right, Meryl, let's put it in the automatic mode and move our part somewhere in the field of view and run it in automatic mode one time. Very good. Good job, Meryl. So let's hang our teach pennant up. Go back to your seat. Good job. All right, so those are some of the steps that we use to establish a 2D single view vision process. Again, key elements, remembering using correct user tool, user frame. Also want to remember that when you establish your or put your calibration grid inside your work cell, before you establish your user frame and do the grid calibration, that it not be moved once it's in place. And also you want your calibration grid at part height or near part height when you do your grid calibration. And you also want to make sure that when you create your teach pennant program that you do call up the user tool that you defined and the user frame that you defined in your vision process. Those are typically the most common errors made in vision programming for your 2D systems there. Okay. All right, good job.